Now, the funny thing was I get so uptight and worried about it. The exams I had to take myself, and I thought, you have nothing writing on this. You know, your career doesn't depend on how you score on this exam, but I still get all uptight. Okay, I'm going to say to start with that we probably did enough with quiz 1 and quiz 3 last time. If you have a few specific questions, let me know and we can bounce back and pick those up. But for now, let's just make a quick run through of quiz 2 and see what you want to talk about. And I will emphasize, oh, I noticed something I thought I should mention. I think 4 and 5, I'll put special emphases on those because those were from the days when, or that day when we were out thanks to the ice. Yeah, okay, so let's go through these. If you want to emphasize some more than others, we certainly can. This first one right here is talking about, well, let's see, 1 and 2 are both about types of structure. So this first one is C, and let me use this as just a way to briefly summarize what each one talks about. Folding of the whole molecule is what you're looking at if you're using the term tertiary. Secondary is local winding or folding, smaller scale. Primary is just your list of amino acids in order. And quaternary, that has its own little niche. And this is just a number. It's the number of polypeptides that you need. So say something like for a fully active protein. Okay, so that's a quick review of all the different levels. This one is C, like I pointed out there. The next one, hydrogen bonds parallel to the direction of the polypeptide backbone. That's talking about stabilizing secondary structure, and besides that, you can even be more specific about it than that. We talked in this class about 2 different versions of secondary structure. There's alpha helix and beta pleated sheet. So which one of those 2 would we be talking about if we said they're running parallel to the backbone? Yeah. Okay. This one, that one, the parallel version is alpha helix. The other option, which the question could be tweaked to this, perpendicular is a beta pleated sheet. It literally folds up and down as if you had a sheet that was folded. Okay, then the next one, I guess that was given away by the answer to the first one. So this would be D, quaternary. Tetramer means it needs 4. So you're talking about a number. It needs 4 polypeptides. Okay, so the next couple here, like 4 and 5, were from a day when you would have looked at a video, which isn't as good as being online. So let me just do a sketch of the way this would have been presented in class, the way it would show up probably as part of these homework problems from the book that the question were mapped to. So the question is, what happens to a reaction? What happens when you've got a catalyst versus not? So here's this whole funny thing right here. This is called a reaction progress diagram, and on the vertical axis you have potential energy. On the horizontal axis you have reaction progress. So anywhere from 0 at the beginning to 100% when you're all done. the typical profile for an exothermic reaction is it starts out somewhere, has to climb a hill as the reactions bang hard together, reactants bang hard, and then you're all done like that. Okay, and then the two questions are, well, what does the catalyst do? All right, the first one refers to free energy. Free energy is the difference between where you start and where you stop vertically. So that vertical distance right there, that's delta H, which is your free energy change. In this case, it's negative here. And that means that the reaction does want to go. Everything in the world wants to fall downhill, including reactants. If they have a way of sensing whether it's better to go downhill, they will take it. Okay, now the other number, well, let me answer the first. The free energy change does what to the free, a catalyst does what to the free energy of a reaction. So does it increase, decrease, or not change? No change. Okay, definitely C. Now, if you put in a catalyst, here's what you do. Maybe something more like this. There's still an activation energy, but this is what you're talking about if you do indeed have a catalyst present. Okay, so a catalyst increases the rate, and here's another way of thinking about this. This is another way the question could be written to kind of get at the same thing. So what does it do to the rate? Well, it increases this. And it does this, put this in a sentence maybe, does this by lowering the activation energy. That means that there's a smaller hill to climb. Yeah, okay, and an example that comes to my mind is probably the most basic biological reaction there is, most important one from this course. Glucose and oxygen goes to carbon dioxide and water. Okay, you all know that much from a freshman bio class. At the same time, you can take glucose and set it in a jar on the countertop in the presence of air, oxygen, and it will sit there for the rest of your life, and you won't be able to tell any difference. In fact, just to make the point once, I don't think I have this video anymore, I tried to see what it would take to set glucose on fire, react it with react it with oxygen. You can throw matches into powdered glucose all day long, and it won't light on you. But what I was eventually able to do was I burn a pile of brush back behind the house every so often. And I got a hotbed of coals built up, and I took some glucose, don't tell the stockroom I did this, but I took some glucose powder from the stockroom and put it on a shovel and dumped it onto the hot coals. And then it would kind of go poof at you. But that's literally how hot you have to get glucose if you're wanting to get it to react with oxygen in the absence of a catalyst. You've got to downright whale on the stuff to get it to react with oxygen. But it's still the same reaction. It's got to climb a big hill in order to go to carbon dioxide and water. And then compare that with what happens in your body. Almost no activation energy thanks to the catalysts in your body. Take it apart just one step at a time. Room temperature and pressure, neutral pH, no hot coals needed, nothing like that. Just totally awesome reaction when it's done in your body. But it's overcoming, that's a different version of the reaction than if you just try to do it without a catalyst. Big hill to climb. That's the difference between enzymes being present and not present. Enzymes are our favorite catalysts, of course. Okay, maybe you didn't need to hear all that, but I'll see if I can find that video. Once we get to the chapter on combustion of glucose in your body, it's useful to have that as a comparison. We do things so mildly with glucose, the other option, keep in mind what the other option is. Throw it on hot coals, get it to do anything at all. Okay, enough on that. So at low concentrations of oxygen, number 6, which protein has the higher affinity for oxygen? I don't know if you remember the curves, but they look like this. One of them takes off very quickly and levels off. The other one takes a little bit longer. Okay, higher affinity for oxygen is which one? Yep. You want it to be this way. And the reason is it's to be used for storage out in the tissues where it's needed. The last thing you need is for you to have a wimpy storage protein so that hemoglobin comes along, and hemoglobin, which is in the business of circulating oxygen, can't even give up its load to the storage protein. Okay, that's not what you want. And the next one, the Bohr effect refers to the fact that hemoglobin's affinity for oxygen decreases in response to what? There's more than one right way to answer this one. Yeah, okay, and which direction?
Decrease.
Yeah. Okay, well, so one way to say it is it changes in response to decreased pH. You could also say, this on scale, or increased. Draw this carefully now. You draw those brackets around protons, that's referring to molar concentration. Either way you want to say that. Decreased pH or increased proton concentration. Okay, and that's a good thing because out in the tissues, that's the way things tend to work, and it makes hemoglobin turn loose. All right, on the next page, there are some statements to make. I'll try not to make these very long-winded. Hydrogen bonds that stabilize helical structure are different from the ones that stabilize pleated sheet. There's more than one right way to say this one. So alpha helix, I guess I'd say something like this. Your hydrogen bonds are, and here's the operative word, parallel to the backbone. And in a beta sheet, it's the opposite, it's perpendicular. All right, some version of that statement. All right, this next one called for a little bit of explanation, a little bit of interpretation, a little drawing. Replacing lysine with arginine in protein doesn't have much effect. And why is that? In your answer, name the interaction that both lysine and arginine can use to stabilize the protein structure. Okay, this would be a good place for dipping into the structure of the amino acids, so you'll have access to this on the exam. So let's look them both up. There's arginine right there, and lysine is right there, next door to each other. So the explanation, it'd be something like this. Both of these amino acids have in their R groups a positive charge. All right, so they're similar in that regard. They're slightly different sized, but the big similarity is they both have a positive charge. And also name the interaction that both lysine and arginine can use to stabilize a protein's tertiary structure. Okay, so the first part is that first statement that I wrote there. Okay, so the name of the interaction that stabilizes tertiary structure, okay, is, and I'll list some of the choices here, knock some of them out, and we'll maybe talk about why the right one is what it is. So you've got a list that would be hydrogen bonding, hydrophobic bonding, salt bridges, and last of all would be covalent bonds. Any one of those, well, all of them are known at some point in nature to hold the whole thing together, the whole protein structure together. These are arranged here in order of, approximately order of increasing strength from weak to strong. So you'd look at those or be thinking of that list, and I hope what you would recognize is a positive charge is one of the main components in a salt bridge. In a salt bridge, you need two partners, one of them positive, the other one negative. So what you would choose here is just say something like that. In your answer, name the interaction, say either one of them can be part of a salt bridge. And why is that? Because of the positive charge that's out there in that R group. It will be looking for a partner R group from somewhere else in the protein to join up to, and its partner should have a negative charge. They'll stick together well if that's the way they're arranged. And then the last one is drawing a polypeptide, small peptide. Do you want to see that? We've done it several times. I'm happy to do it again if you want to. Kind of up to you. I get the feeling you've kind of seen this enough, right? In which case, that's good, and I will leave with just one plea. NCC, NCC, NCC. Start by getting that much right. Get your back on it. If you get that much, it's usually pretty good from there on out. Okay, is there anything from this quiz or from the other two? The graded ones are here. I don't think I even wrote the scores. If you're here, you were given full credit, right? Yes.
Isn't there supposed to be an O at the end of that?
There would be, yeah. Let me finish it off. So there's that, and then here's a carbonyl, and here's a carbonyl. Out here at this end, there's a positive charge. The interior nitrogens all have a hydrogen, and the interior carbons all have a hydrogen. There's alpha, there's alpha, there's alpha. And that just leaves you then with 3 R groups. Okay, that was good. Any more? Well, all right then, let's call it a day. No other questions. And I will see you on Monday. If things work well, you study efficiently for your exam by looking at your quizzes and the review version of the quizzes that we've done here in class.